Welcome to ERC Tipsnology. In this video, we will be talking about interrupt programming. First, let's talk about the definition of interrupt. An interrupt is an external or internal event that interrupts the microcontroller to inform it that a device needs its service. And this means that the interrupt is trying to stop the microcontroller from doing its task and asking it to do some service for the device. So, an interrupt again is an external or internal event that interrupts the microcontroller to inform it that a device needs its service. Now, a single microcontroller can serve several devices in two ways. The first way is through interrupts, and the second way is by polling. Now, for the interrupts or the interrupt method, whenever any device needs the service of the microcontroller, that device will notify or inform the microcontroller by sending it an interrupt signal. Upon receiving the interrupt signal, the microcontroller interrupts whatever it is doing. So it will stop whatever it is doing and it will serve the device that needs its service. Now, the program which is associated with the interrupt is called the ISR or Interrupt Service Routine. We can also call it interrupt handler. Now, on the second way, which is the polling method, the microcontroller will continuously monitor the status of every given device. And when the conditions are met, then it will perform the service. So after that, it moves on to monitor the next device until all the devices are serviced. So the polling can monitor the status of several devices, not just one, and serve each of them as certain conditions are met. But there's a problem with this. The polling method is not efficient because it will waste much of the time or much of the microcontroller's time by checking or monitoring or polling the devices that don't really need its service. Now, the advantage of interrupts is that the microcontroller can serve many devices, but not all at the same time. But the good thing here is that each devices can get the attention of the microcontroller based on the assigned priority. So, unlike in polling where the devices will really be like in line or waiting for its turn to be monitored before the microcontroller will know its situation, whereas in interrupt method, each devices can get the attention of the microcontroller anytime based on some priorities. Now, for the polling method, it is not possible to assign priority because it will check all or every device in a round robin fashion. It means that it will be like one by one, or after checking one device, it will check the next and then the next. It's like you are in line or in a queue before you can be serviced by the microcontroller. It needs to be like checking one at a time in a round robin fashion. Now, the microcontroller can also ignore or mask a device request for service. This is not possible for the polling method. Now, for every interrupt, there must be an interrupt service routine or ISR, or this is the interrupt handler. So, what will happen whenever there's an interrupt request, then when an interrupt is requested or invoked, the microcontroller will run the particular interrupt service routine or ISR. And for every interrupt, there is a fixed location in memory that holds the address of the ISR. And the group of memory locations set aside or to hold the addresses of the ISRs is called as interrupt vector table. So this interrupt vector table contains the uh, group of memory locations set aside to hold the addresses of ISR. So there are 6 interrupts and they are the following. First, we have what we call as reset. This is a power up reset. We also have timer 0 interrupt and timer 1 interrupt. So there are 2 interrupts set aside for the timers. And then we also have 2 interrupts that are set aside for external interrupts or hardware external interrupts. This can be found on P or port 3 bit 2 or P3.2 and port 3 bit 3 or P3.3. And we call it as INT0 and INT1. We can also call it EX1 or EX2 to represent external interrupt. Now the last one is the serial communication. It has a single interrupt that belongs to both receive and transfer. So again, these are the 6 interrupts: reset, external hardware or interrupt 0, timer 0 interrupt or TF0, external hardware interrupt 1, timer 1, TF1. This is serial COM, RI, and TI. These are the ROM location of the interrupts. For reset, we have 0000. For external interrupt, we have external HW int 0 0003. And then we have timer 0 interrupt 000B, external hardware interrupt or INT1 0013, timer 1 interrupt 001B, and serial COM 0023. Again, the reset is on pin 9 and the external interrupt 0 and external interrupt 1 are on pins number 12 and 13 respectively, or we also call it as port 3 bit 2 and port 3 bit 3. But take note that the timer 0 here is having an address of 000B and timer 1 is having an address of 001B. Now, upon reset, all interrupts are disabled or ignored by the microcontroller. This is called masking. It means that none of these devices will be responded to by the microcontroller if they are activated. So the interrupts are activated or enabled when we put a number 1 or a high to these interrupts. You will see that later on when we discuss about the next parts. Now, the interrupt must be enabled by the program or by the software in order for the microcontroller to respond to them. And there is a register called IE. IE stands for interrupt enable, and this is responsible for enabling or unmasking and disabling or masking the interrupts. Again, when we say mask, it means ignore, or the microcontroller will never mind the device. And when you say enable or unmask, it means that the microcontroller will be doing whatever the interrupt is asking it to do. So that's why it will be enabled, or it will inform the microcontroller that it needs its help. Now, this is the representation of the interrupt enable register. We have data 0 up to data 7, or D0 up to D7. So we have 8 bits that we can put in the IE or interrupt enable register. We have the EA or the enable all, which must be set to 1 in order for rest of the register to take effect. So what we mean here is that EA must be equal to 1 before you can use any of the 6 registers or any of the 6 interrupts here. And let's start with the ET2. ET2 is called the timer 2 interrupt. This is the on position number 5, D, or number D5 or data 5. So from data 0, this is data 5. Or if we can count from 0, 0, 1, 2, 3, 4, 5. So if you want to use the timer 2, we can have the timer 2 or the external interrupt timer 2. We can put 1 to ET2. Now for the ES, this stands for the serial port interrupt. If you put 1 on ES, then the serial port interrupt will be activated or enabled. If you put 1 to ET1 or the timer 1 interrupt, or we shall say ET1 equals 1, then you will activate or enable the timer 1 interrupt. If you want to enable the external interrupt 1, EX1, then you have to put 1 on EX1. If you put 1 on ET0, the timer 0 interrupt will be enabled. And the last one, EX0, if you put 1 to EX0, it will be enabled. This is the external interrupt 0. So these are the interrupts that we can use. So again, we have the external interrupt 0 or EX0, external interrupt 1 or EX1, timer 0 interrupt, this is ET0, timer 1 interrupt, this is ET1. We also have the serial interrupt or the ES. We have the timer 2 overflow or capture interrupt, but this is only applicable to 8952 or 8952. And then we have the IE.6, which is not implemented. So this bit here can be used for a 0 or 1, or you can put 0 or 1, but it's not really used. And on EA, this is the most important. You have to put 1 here before you put any activation 1 here on the 6 interrupts. Now, to enable an interrupt, we must take the following steps. Again, the IE register EA must be set to 1 or to high first to allow the 6 other registers to take effect. It means that even if I activate any of the 6 interrupts here, it will not work because if you put EA equals to 0, so EA must be equal to 1 first. Secondly, if you put EA equals 0, then none of these 6 interrupts bits will be responded by the microcontroller. Now let's have an example. Let's try to enable the serial interrupt, the timer 0 interrupt, and the external hardware interrupt 1, EX1. So to do that, we have to we can use one line command like this, IE equals 0x96. Take note that 9 is hexadecimal number 9, and if you change it to binary, that will be equal to 1001. So in other words, when we go back here, if we go back here, this will become EA equals 1, and this will be 0, this will be 0, and this will be 1. So what will happen is like the ES or the serial port interrupt will be enabled here, and the EA will be equal to 1. It means that for any activation number 1 that you put here, it will not be effective unless you put EA equals 1. So we will be forced to put 1 on EA, and to do that we have to put 1, 0, 0, and then you can put 1 on ES if you want to activate ES. Now you will see here that the answer here is 9. That's why it's 1001. Now for the number 6, this is hexadecimal 6. So if you convert this one to a binary, 6 will be a 0, 1, 1, 0. So if you go back to the IE or interrupt enable register, it would mean that ET1 will be 0, EX1 will be 1, and ET0 will be 1, while EX0 will be 0. Again, 0, 1, 1, 0. Now, if we do that, that's binary 0, 1, 1, 0. That's equal to 6 because this position is number 4 and this position is 2. So 4 plus 2 in binary, that's 6. So that will be binary 0, 1, 1, 0 is hexadecimal number 6. So in other words, we are activating or enabling the external interrupt 1 and the timer 0 interrupt, which is precisely what we need to do here. We have to activate or enable timer 0 interrupt and the external hardware interrupt 1. Again, the external hardware interrupt is EX1 and the timer 0 interrupt is the by putting 1 on the ET0. That's why EX1 is 1 and ET0 is 1. So this will be 0, 1, 1, 0. So to make it summarized, this will be 1, 0, 0, 1, 0, 1, 1, 0. So EA will be equal to 1, ES will be equal to 1, EX1 equals 1, and ET0 equals 1. And we can do that by simply putting 0x96 to our IE. So again, 96 means 1001, 0110. Another solution, but longer, will be to use 4 lines of code, which are EA equals 1, semicolon, ES equals 1, semicolon, EX1 equals 1, semicolon, and ET0 equals 1. So in this way, we have to enable all equal to 1 and serial port interrupt equals to 1. External interrupt 1 will be equal to 1 to enable it, and timer 0 overflow interrupt will also be enabled by ET0 equals 1. So note that the EA equals 1 is like enable all bit will be equal to 1. ES equals 1 means that the serial port interrupt will be equal to 1 or activated or enabled. EX1 equals 1 means that the external interrupt 1 will be enabled, and ET0 equals 1 will be like timer 0 overflow interrupt will be enabled. Now for letter B, we have here a task to disable or to mask or to ignore the timer 0 interrupt. So if you analyze the timer 0 interrupt is located on ET0. So to disable this, we have to put 0 to ET0. So the answer here is to make ET0 equal to 0. So let's see the solution on letter B. So ET0 equals 0. Now for letter C, we have to show how to disable all the interrupts with a single instruction. Of course, if you don't do the single instruction, all you have to do is to put EA equals 1, ET2 equals 0, ES equals 0, ET1 equals 0, up to EX0 equals 0. But if you do that, you will be needing to write 2, 4, 6, 7 lines of codes. So in other words, this is not what we want to do. We want to show how to disable all the interrupts by simply using a single instruction. So as you can see in the solution here, the EA you just need to put equals 0. So EA equals 0 will disable all the interrupts here. And you don't need to put EA equals 1. You have to put EA equals 0. That's it. No need to write 0 to each of the 6 interrupts. Now, talking about the TF or timer flag, this is automatically raised or becomes 1 when the time rolls over. Remember that rolling over means you have reached, or the timer have reached the maximum count that it can do, and then it will go back to 0. That's why it's called rolls over or rolling over. Now, in polling timer flag, we have to wait until the timer flag is raised. Again, it will only be happening when the timer rolls over. And how will the timer rolls over or roll over? It needs to wait for the polling method to finish monitoring each of the devices one by one. So it will take a long time before the TF becomes automatically one. The problem with this is that, as I have said, that the microcontroller will be checking or monitoring each of the devices. So it will be like tied down while waiting for the TF to be raised, and it cannot do anything else. Now, in the interrupt method, it solved this problem because it will avoid tying down the controller. It means that the microcontroller is free to do or uh, to go to a certain timer interrupt service routine, and it does not really need to wait for a long time because it can do whatever it is doing while nothing or no device is asking for its help. Now, if the timer interrupt in the IE register is enabled, whenever the timer rolls over, the TF is of course raised. So the microcontroller is interrupted in whatever it is doing, and it will jump directly to the interrupt vector table first, of course, to before it service the or to be able to service the ISR, because the interrupt vector table contains the address of the ISR to be serviced. Now, in this way, the microcontroller can do other things until it is notified that the timer has rolled over. And again, it will be notified by the timer flag when it is raised. So the timer flag 0 here, when it becomes 1, the timer 0 interrupt vector here, for example, contains 000B. So it will jump to 000B. Now, if the timer 1 is used, timer flag 1 will be 1. Then the timer 1 interrupt vector, let's say, has 001B. So it will jump to this timer 1 interrupt vector that contains this address. Now, the 8051 again has two external hardware interrupts. As I have said before, that it is on pin 12 or port 3.2 and pin 13 or port 3.3 of the 8051. And this is also called INT0 and INT1. Again, the INT0 is on port 3.2 or pin 12, and INT1 is on pin 13 or port 3.3. And these are used as external hardware interrupts. Now, the interrupt vector table locations 00038 and 0013H are set aside for INT0 and INT1. So if we'll go back to the table that I have shown you here, the INT0 is 0003 and the INT1 is 0013. And these are expressed in hexa. So the ROM location, which has 4 hexadecimal numbers, means that we have 16 binary digits or 16 bits address. Now, when the 8051 is turned on or powered up, the priorities are assigned according to the following. In reality, the priority scheme or the priority it is following is nothing but an internal polling sequence in which the 8051 will check or monitor the interrupts in the sequence listed here and responds accordingly. So it will first check the external interrupt 0 or INT0, and then followed by TF0, then INT1, and then TF1 before checking the serial communication. This is upon powering up, so the priorities are assigned according to these priority positions. So having the external interrupt INT0 as the highest and serial communication as the lowest. Now, the 8051 compiler have extensive support for the interrupts, and they assign a unique number to each of the 8051 interrupts. So the most important to remember here is the timer interrupt 0, whose number is 1, and timer interrupt 1, whose number is 3. Usually in some programmers or programs, the timer interrupt 0 is supposed to be 1, but they are putting 0 in the interrupt number in the program. You will see that later on when we discuss about some example programs. Now, the timer interrupt 1, which is supposed to be number 3 in the program, they are writing interrupt 1 just because it's timer 1. Now, for the other numbers, 0, 2, 4, and 5, these belongs for interrupt, external interrupt, or INT0. For external interrupt 1, INT1. And then for serial communication, the number is 4. And for timer 2, which is only available in 8052, that's number 5. Now, let's have an example here. Let's write a C program using timer 0 interrupt that continuously gets a single bit of data from port P1.7. So it means that port 1, bit 7 will be used as an input port. And we can put here a 1 or a 0. And this can be possibly done by using a switch. Now, after putting here 1 or 0 in port 1.7, it will send it to port 1.0. So it means that the port 1.0 will receive whatever digital 1 or digital 0 you put on port 1.7. So the port 1.7 will be the input to the port 1.0. And at the same time, we will be creating a square wave of 200 microseconds period. So if I want to have a square wave, we should produce a 100 microsecond positive waveform at the positive side and a 100 microsecond negative square wave on the negative side to make a total of 200. Therefore, the positive waveform will be taking 100 microsecond and the negative square waveform will be taking 100 microseconds too. And this will be on pin P2.5. Now, we have to use timer 0 mode 1 to create the square wave and the timer 0 interrupt for the interrupt. Now, let's assume that the crystal frequency is 11.0592, and because of that, if we divide 12 divided by 11.0592 megahertz, the answer will be 1.085 microseconds. Now, again, the solution here is to have the period divided into 2. So, 1/2 of the period is 100 microseconds. And so the delay will be 100 microseconds. After determining the delay of 100 microseconds, we will be calculating the initial values for 100 microseconds. And because this is timer 0 and we are using mode 1, that would be 2 to the power of n minus 1, that's 2 to the power of 16, minus 1, that will be 65,536, minus 1, that will be 65,535. I think I missed writing minus 1 over here. So kindly do the correction, 2 to the 16, minus 1. And then we will subtract 100 microseconds divided by, actually this is 12 divided by 11.0592. And we will be getting 1.085 microseconds. This is 12 over 11.0592. I did not write it anymore here, but the answer will be 1.085. So if you divide these two, the microsecond will be cancelled and we will be getting 92.17. And subtracting it from 65,535, we got a 65,442.83. And let's drop the integer value, so it will be 65,442, and convert it to hexa, it will be FFA2. And so the TH0 will be FF and the TL0 will be A2. That will be the initial values of the timer 0 registers. Now, let's make the program. You can see on line number 1, the usual include the with the header file reg51. And then on number 2, line number 2, we declared the SW to represent the port 1.7 or 1 caret 7, and this refers to the input, and we use SW to just simply say that this is like a switch. And then we have another S bit IND P1.0. So the digital input here, whatever you put on P1.7 must go to P1.0 or P1 caret 0. This is another variable IND that represents P1.0. And for the square wave, we used wave as our variable name to represent the port P2.5 or P2 caret 5. Now, the timer 0 here is the interrupt service routine. In other books or text, on our textbook or other books, they usually put here timer 0 ISR. But you can also cancel the letters ISR. Instead, we just put here timer 0, but this is not really a timer. This is an interrupt. So we put void timer 0 void. So if here it says that the timer 0 interrupt, we put here timer 0. If it is timer 1 interrupt, we put timer 1. Although you can use any name that you want, we can still make this shorter by using T0 instead of timer 0. And then here we have interrupt number 1. We did not put 0, although this is timer 0, because the interrupt number assigned to timer 0 interrupt is number 1. So if you have forgotten that, this is the numbers I'm talking about, that the timer interrupt 0 has a number of 1 and timer interrupt 1 has a number of 3. So going back to our discussion of the program, void timer 0, void interrupt 1, this is the function or the ISR or interrupt service routine for our timer 0 interrupt. And the number is 1 because this is the number assigned to timer 0. Now inside this line number 6 and line number 8 is a wave equals tilde wave. So this tilde sign means we will take the opposite value of wave, and wave is P2.5 or port 2 bit 5. And it's like if it is 0 in the beginning, then it will become 1, and then it will become 0, and so on and so forth. Now on line number 10 up to line number 21, this is the main function. And in line number 11, we declared the port 1.7, which is represented by SW as equal to 1. Why 1? Because this is an input. Now, if the port is an output, we have to put here 0. But because the port 1.7 or P17 or the SW will be used as an input port, we have to place here 1. Then we have the timer mode equals to 0x01. Remember that the first number here, 0, is not timer 0. It's mode 0. And the number here, 1, this means mode 1. So in other words, the number 0 means mode 0 and the number 1 means mode 1. And the position here where 0 is placed is what we call as timer 1. And this position here is called timer 0. So don't be confused with that. So it means that this 0 can be 0, mode 1, mode 2, mode 3. So this can be 0, 1, 2, or 3. And here, this number 1 can also be 0, 1, 2, or 3 to represent the modes of the two timers. But take note that the first number here that I'm pointing at, 0, this is not timer 0. This is timer 1. And the number 1 here is timer 0. So don't think that these numbers represents the timer. This represents the mode. That's why this is mode 0 and mode 1. And because the question here says that we have to use timer 0 in mode 1, this means that the number on the right here must become 1 to tell that it's mode 1. And the position here is still timer 0. So to have a complete answer, this timer mode is actually timer 1 mode 0, timer 0 mode 1. And we can use timer 0 mode 0, timer 1, timer 1 mode 0, and timer 0 mode 1. Now, the TH0 is 0xFF because that's what we have calculated over here on the left side. And TL0 is equal to 0xA2 because that's what we have calculated here on the left side for TL0 initial values. Now, the IE is equal to 0x82 because the 8 here represents the hexadecimal number 8. And if you convert it to binary, that will be 1000. So 8 is 1000, and the number 2 here is hexadecimal 2. That would be 0010. So the hexadecimal 2 is actually 0010 in binary. So putting them together, this timer 0 will this enable interrupt enable will become 1000 0010. So this is what will happen. In other words, these 8 digits here, one will go to EA and one will go to timer 0 interrupt. So take note, 10000010. If we will go back to our IE register, we will see here that this is like 10000010. So EA equals 1 to make sure that whatever you do in the 6 interrupts will take effect. And what have we done? The ET0, we made it 1. Therefore, we are trying to enable timer 0 interrupt. That's why we put that one. Now, if we want, you can also say or write EA equals 1, ET2 equals 0, ES equals 0, ET1 equals 0, EX1 equals 0, ET0 equals 1, EX0 equals 0. You see, that's too difficult to do because you will be using 7 lines of codes instead of simply putting 1 line of code. That's why it's better that we master the use of hexadecimal numbers here, like 82, if we want to control the timer 0 interrupt. Now, the next line, 16 and 17, is not that important. This is just a comment that where I'm just telling you that the ET0 or timer 0 interrupt will become 1 or enabled, and EA or enable all will become 1 also, while the other 4 interrupts will be unaffected. Now, the while one here will be doing repeatedly or continuously the command IND equals SW. So if you will remember, the IND is port 1.0, so it will take its value from the switch here, which is coming from port 1.7. So if port 1.7 has 0, then port 1.0 will also have 0. So the IND variable for port 10 or P10 will depend on the value of P17 or P17 as required in the question, where the bit of data will be from P1.7 and it will go to P1.0 continuously or repeatedly. And at the same time, you will see here that we are producing a square wave here by making the value of P25 or P25 to be 0, and then 1, and then 0, and 1. And that's the way to create the square wave. Now, in the next example, we have how to generate the 50 millisecond delay. So based on our calculation here, we have to use the formula. I'm sorry for this, but we was not able to put -1. So 2 to the power of n minus 1 minus delay divided by the quotient of 12 divided by 11.0592, and this will be giving us 1.085 microsecond. So the delay that we want is 50 milliseconds, but we cannot divide 50 milliseconds to microseconds. So you have to make this also microseconds so that we can cancel the microseconds symbol here or unit. And 65536 minus 1, which is 2 to the power of 16, will be 65535. Again, this formula 2 to the power 2 to the n should be 2 to the n minus 1. That's why we got here 65536 minus 1, we have 65535. And if you continue calculating this, we will get the answer of 65535 minus 46082. We just drop the decimal point here. We can have it as 46082 and we will get 19453. This is the decimal answer, and in hexa that would be 4BFD. So our TH0, if we are using timer 0, oh, so we are using timer 1, so TH1 will be 4B and TL1 will be FD. Again, the 2 to the power of n can be 13, 16, or 8, depending on whether you are using mode 0, 1, or 2, respectively. Now, also the delay 50 milliseconds is just given here as 50, but we may have a different value for our delay. It can be given as a different value. So the TH and TL is not always 4BFD. It can change. Now, if you will be looking at the program here, again, on line number 1, this is just a comment that we want the P0.0 to blink the LED every 50 milliseconds using timer 1 interrupt. Now, you will notice at line number 7 that the void here is followed by timer 1 underscore or underline ISR. So it's not necessary to put ISR, or it's not necessary to put the name completely like timer 1. We can simply put T1 here instead of this long name. But let's just say we use timer 1 ISR as our interrupt service routine program, or ISR program or function. This will be from line number 7 to line number 12. So this is what the interrupt wants the microcontroller to do. And because we are using timer 1, the interrupt number that you will put here must be 3. And sometimes there's a mistake, like we are writing timer 1 and then we will put here interrupt 1. So it must be interrupt 3. Why? As I have mentioned before, the timer interrupt 1 is, or the timer interrupt 1 must have a number 3. And the timer interrupt 0 must have the number 1. So it's a little confusing, but with more practice or by writing programs in interrupts, you will be familiar with it. So timer 1 ISR interrupt 3. This means we are using timer 1 interrupt function or interrupt service routine. And it will be doing 3 things. The port 0.0, which contains the LED, or maybe we are connecting an LED there. That's why we use the word LED, although we can still make this P00 if we want instead of LED. But since it's LED, then till the LED means that the LED at P0.0 will be blinking, or it will be turning on, turning off, turning on, turning off, because tilde means take the opposite of the last value of LED. Now, TH1 is equal to 0x4B and TL1 equals 0xFD. You can write also TL1 first before the TH1, like TL1 equals 0xFD followed by TH1 equals 0x4B. So it does not really matter. But again, this will be like blinking the LED every 50 milliseconds delay. That's it. This is what the timer 1 ISR wants the microcontroller to do. And you can see that the timer 1 ISR was also placed before the main. Now, if you put the timer 1 ISR after the main, then you still need to declare void timer 1 ISR void here and with semicolon. Actually, you can cancel the void here. You may cancel that, but if you put void inside the bracket or the parenthesis, it will also be okay. Now, the main function here has number 16 up to 23 to be repeated. And you will notice here that we make the port P0.0 or the LED equal to 0 just to say that it's an output port. So if it is an input port, then we will be using 1, just like what we have done in the previous example where the P1.7 was made to become 1 because it's an input. But in this case, the port P0.0 is an output, so we need to put 0 in it. Now, the timer mode is equal to 0x10, and this number 1 is for timer 1, and number 0 is for timer 0. It just happens that it also has the mode 1 and the mode 0. So, but it does not mean 1 here is timer 1. This means mode 1, and the 0 here means mode 0. And without looking at these numbers, it will still be timer 1 on the first number here, whether it's 0, 1, 2, or 3. And whether this is 0, 1, 2, or 3 also, this will be timer 0. So to make this a complete explanation, the T mode is actually mode 1, timer 1, and mode 0, timer 0. But you can use timer 1, mode 1 only. Now, TH1 is equal to 0x4b and TL1 is equal to 0xFD. This is loaded to our TH1 and TL1. You can also write TL1 first before TH1. Now, to start the timer, we can put TR1 equals 1. It will start timer 1. Now, if we are using timer 0, you have to put here TR0. Same with TH0 and TL0 over here. So everything must be 0 here if it is timer 0. But this is timer 1 interrupt, so we put TH1, TL1, and TR1. And this is equal to 1 because we want to start the timer 1 or we want to turn on timer 1. ET1 equals 1 so that we can enable timer 1 interrupt. Where is ET1? So let's go back to our IE register. So this is ET1, and ET1 means timer 1 interrupt. So this time we want to put 1 to ET1, and you will notice that the program did not use a one line of code for our interrupt bits. Instead, we simply put 1 on the value of ET1, and EA we also make it equal to 1. We can put EA equals 1 first and then followed by ET1 equals 1. For the others, we don't need to make it 0 because it's understood to be 0. Now, while 1 semicolon will just be repeated forever, doing nothing. Now, because we run the timer 1 or we turn on timer 1, and then due to that, we have also activated the after that, we also activated timer 1 interrupt. Then the timer 1 ISR will make the LED to take the opposite value, and then it will go back again here to the main function and go back again to timer 1. In other words, this will be blinking our LED. But take note that the TH1 here and the TL1 here can be TH0 or it can be TH1, TL0, TR1, depending on what timer number you are using. So if you're using timer 0, all of these ones must be 0. Now in this example, we used also interrupt number 3. Although the name of the timer is 1, do not put here interrupt 1. We have to put interrupt 3 if it is timer 1 because that number 3 is the assigned timer interrupt 1 number 3. And timer interrupt 0 is number 1. What else? In the program also, we see that the interrupt 1 is used for timer 0 in the previous example. And if you want the T mode, the first letter N is always timer 1, and the letter M here is always timer 0. So if you have T mode equals 0x23, that's timer 1, mode 2, timer 0, mode 3, 3, 1, timer 1, mode 3, timer 0, mode 1, and so on. So if we have 1, 0, that's timer 1, mode 1, and the 0 here means timer 0, mode 0. Now let's say that the interrupt, let's make our C program that will generate interrupt every 50 seconds to blink the LED at port 0.0, and this time let's use only timer 0 interrupt. So we will be doing the same calculation the same way, and let's say we already know that in the previous example, 4B FD, TH will be 4B and TL will be FD. So in our program, the only difference is that the interrupt number here is now 1. Although we put timer 0, this is interrupt 1 because going back to our table, the timer interrupt 0 or timer 0 interrupt is number 1. So in this example, the timer 0 ISR is interrupt 1. And again, the LED will be blinking like in this way, and the only changes here is the number 0, because before it was number 1, TH1, TL1, now it's TH0, TL0, TR0, ET0. It will be the same, but because we want to use timer 0. So you have to understand that when you are using timer 0 interrupt, this must be zeros. Okay, so that's the note or what you need to remember. The timer 0 interrupt number is 1, while the timer 1 interrupt number is 3. Now, TH0 and TL0 values are not always 4B and not always FD. Again, it depends on the mode that you are using and the calculations. Now, there are 4 modes. Remember, mode 0, mode 1, mode 2, and mode 3. And each of them has different numbers of bits. Now, example number 3, make an 8051C program that will generate interrupt every 50 milliseconds to blink an LED at P0.0. And let's use timer 0 interrupt and timer 1 mode 1 for the time delay. So as you can see here, we are combining the timer 0 interrupt with the timer 1 mode 1 for the time delay. Let's say we have the same calculations for the initial values of TH and TL. We have 4BFD again. And let's just look at the program here. You will notice that the name of the timer here is timer 0, ISR interrupt 1, but you will notice the appearance of timer 1 mode 1 delay here. And remember that the timer 1 mode 1 delay here will be using TH, TL, TR, TF here inside it. Actually, we can also put T mode here, which will be equal to the timer mode, but in the main, you will notice that I already have T mode equals to 0x11. Now, what does this 11 means? What do this 11 means? It means mode 1 for timer 1 and mode 1 for timer 0. So in this case, we are using both timer 0 and timer 1. We use timer 1 mode 1 for the delay, and we use timer 0 interrupt. So we have timer 1 mode 1 for the time delay, and we use timer 0 for our interrupt, but it's in mode 1 also. So in the timer 0 interrupt, we are doing here LED equals tilde LED, and then we will call the T1 M1 delay, and this is the T1 M1 delay, which will be providing the 50 milliseconds delay. And then after that, it will go back here, and you will notice that the TR0 equals 1. Again, it will start the timer 0. AT0 equals 1. It will enable the timer 0 interrupt or activate the ET0, and EA equals 1 will enable global interrupt. So we can also put EA equals 1 first before the ET0 equals 1. And while 1 will repeat forever doing nothing. But then because we put here TR0 equals 1, it will always start the timer 0. And because we put ET0 equals 1, it will always start or enable the timer 0 interrupt. Now remember here that we have three functions. We have the timer delay function, we have the interrupt delay function here, timer 0, and we have the main function. So we have three functions here. Again, so that we will avoid declaring the timer, the timer interrupt function or the timer delay function, we can put the functions before the main, so that we don't need to have an extra two lines, because in other textbooks the functions for this are placed after the main. Now again, if you put these functions before, you don't have to declare them again at the top. So timer 0 ISR here again uses timer 0 mode 1, and this is our interrupt function that has the command for blinking the LED and calling the timer 1 delay. Now the main contains the declarations for as whether this is input or output. So this is output for the LED, which is on pin number, which is on port P. Is it declared here? Where's that part? That the LED is S bit P0.0. I think it's not given here. So we have to put here on number 6 S bit LED equals P0.0. So that's the correction on this part, number 6. We have to put S bit is equal to P0.0 before the equals P0 caret 0, I mean. So that's a correction there. Maybe we can put it later on. So in this example, we are using two timers, timer 1 and timer 0 for our timer delay and interrupt delay. So we are combining what we learned about timer and what we learned about interrupts. So that's it. I think this is the last example. So I hope you like this long video and you learned something about timer programming. This is the most extensive explanation that we can do, so that you will be understanding timer programming. Thank you so much. I hope that you will be subscribing to our YouTube channel and share it, so that we can help other people to understand about 8051 microcontroller programming. Please subscribe and share the video and like it towards our goal of getting 1,000 subscribers. Thank you so much. Bye-bye.